Swayam Prabha. Digital India. Educated India.
We are looking at axisymmetric elasticity problems. In the last class we looked at axisymmetric linear triangular element. Basically 3-dimensional elasticity problems involving axisymmetric geometry and loading can be treated as 2-dimensional problems, and in the last class we looked at the governing equations, differential equations, and also we looked at how to derive finite element equations for a linear triangular element. We will continue with that, and before we do that let us look back what we have done in the last class. So basically 3-dimensional elasticity problems involving axisymmetric geometry and loading, as shown in the figure here. Here a typical situation with z axis as axis of revolution is illustrated in the figure. For this kind of typical situation, 3-dimensional elasticity problems can be modeled as 2-dimensional problem. And one more important thing is, for axisymmetric problems the structure, loading and material properties must be symmetric about axis of revolution. Here in this particular situation that we are looking at, z axis is axis of revolution. So we can model this 3-dimensional problem as axisymmetric problem only if structure, loading and material properties are all symmetric with respect to the axis of revolution. Even if geometry is symmetric about the axis of revolution, or the structure is symmetric about the axis of revolution, if loading and material properties are not symmetric, then we cannot use this axisymmetric model. An axisymmetric stress analysis problem can be formulated in terms of two displacement components, u and w. U is displacement component in the radial direction r, and w is the displacement component in axial direction z. These two are similar to u and v, u for displacement component in the x direction, v for displacement component in the y direction that we used for plane stress, plane strain problems. And here for axisymmetric problems, because of symmetry, all the stress components are independent of theta. Stresses and strain components of interest are as follows: 4 components of stresses, sigma r, sigma z, sigma theta, tau r z. All these components are put together in a vector denoted with letter sigma. Similarly strains, epsilon r, epsilon z, epsilon theta, gamma r z, put together in a vector denoted with epsilon. So 4 components of stresses, 4 components of strains. And under small displacements and strain assumptions, strain displacement relation can be written as follows. And here please note that epsilon theta is having r in the denominator, that is epsilon theta is going to go to infinity as r tends to 0. So note the singularity in epsilon theta as r goes to 0, and we need to take care of this during numerical implementation of axisymmetric finite elements, numerical implementation of axisymmetric finite elements must take this singularity into consideration. And next we need to know the constitutive matrix assuming linear elastic material behavior. Stresses and strains are related via this equation sigma is equal to C times epsilon, where C is the constitutive matrix which is going to be a function of two material parameters Young's modulus and Poisson's ratio. For axisymmetric problem, constitutive matrix is going to be 4 by 4 in dimension because there are 4 stress components and 4 strain components. And comparing these equations that we just looked at for axisymmetric problem with plane stress plane strain with the equations corresponding to plane stress plane strain conditions, it can be seen that two problems are very similar, and only thing is primary unknowns of axisymmetric problem are u and w, whereas for plane stress plane strain problems the primary unknowns are displacements in the x direction and displacements in the y directions u and v. So, before we derived axisymmetric derived finite element equations for axisymmetric linear triangular element in the last class, we also looked at potential energy functional. So, potential energy functional can be written similar to that what we have written for plane stress plane strain problems, because both problems are looking similar except the displacement components are different. So, potential energy functional for axisymmetric problems can be written as follows: potential energy functional pi is function of u and w, where u is displacement component in r direction, w is displacement component in z direction. So, potential energy functional pi is u minus w. The definition of u and w are similar to that for plane stress plane strain problems. U is strain energy, W is work done by the applied forces. So, now we need to look in detail how to calculate strain energy for axisymmetric problems and work done by the applied forces for axisymmetric problems. So, strain energy is given by this half volume integral epsilon transpose sigma, and this since we are dealing with axisymmetric problems, we can integrate this with respect to theta going from minus pi to pi, and when we do that, this strain energy becomes an area integral or surface integral. So, work done by the next quantity that we require is work done by the applied surface forces. Work done is given by displacement component in r direction times traction in r direction, displacement component in z direction times traction component in z direction. So, if T r T z are components of applied forces in r and z directions, work done by the forces is given by this. Again, since this is an axisymmetric problem, we can integrate with respect to theta going from minus pi to pi, and then this integral of work done by the distributed surface forces reduces to a line integral. So, potential energy functional is given by strain energy minus work done by the applied forces. Strain energy is basically area integral. We need to integrate over the surface area of axisymmetric model, and work done by the distributed forces, we need to evaluate line integral along the side or edge along which surface forces are prescribed. If specified concentrated forces or body forces are present, work done by these forces can be computed in a similar manner. So, basically all this portion we covered in the last class. Just for brief review, I went through this once again. So, now let us look at derivation of finite element equations for a quadrilateral element, X symmetric 4 node isoparametric element. A 4 node quadrilateral element is shown in the figure. All the displacement components at all nodes are shown. And each element, each of this quadrilateral element is actually a ring with quadrilateral representing its cross section, because we are dealing with problem which is obtained by revolution about z axis. So, the element equations can be derived using isoparametric mapping concepts that we looked at earlier, and for that we require a parent element. So, on the right hand side a parent element is shown in the figure. That parent element is looking similar to what we used for plane stress plane strain problems, 4 node parent element with nodes, with all the 4 nodes at 4 vertices of square. The coordinates of each of the nodes are also indicated in the figure. Note that each element is actually a ring with quadrilateral representing its cross section. Element equations can be derived using isoparametric mapping concept. So, the trial solutions can be expressed in terms of shape functions of the parent element and displacement components at each of the 4 nodes in r and z directions. So, this is how we can calculate displacement component in r and z directions at any point, once we know the displacement components at all the 4 nodes using parent element shape functions, where parent element shape functions are similar to that we already looked at for plane stress plane strain problems. Basically these shape functions can be obtained using Lagrange interpolation formula in S and T directions. And now isoparametric mapping. Using isoparametric mapping concept, we can write the coordinate r at any point in terms of coordinates of all the 4 nodes, radial coordinates of all the 4 nodes, and also if you know the parent element shape functions. Similarly, z coordinate can be written in this manner, and these two equations we require for calculating Jacobian and determinant of Jacobian. Basically Jacobian consists of partial derivative of r with respect to S and t, partial derivative of z with respect to S and t. So, once we have these two equations, we need to take partial derivatives of these two equations with respect to S and t, and then we can calculate what is Jacobian matrix J and also determinant of J. So, Jacobian matrix consists of components: partial derivative of r with respect to s, partial derivative of z with respect to s, partial derivative of r with respect to t, partial derivative of z with respect to t, and determinant of j is given by this, and for this we require partial derivative of r with respect to s, which can easily be obtained from the previous equations by taking partial derivative of shape functions n1 to n4 with respect to s. Similarly, by taking derivatives of shape functions n1 to n4 with respect to t, we can easily write partial derivative of r with respect to t. So, similar expressions, that is partial derivative of z with respect to s, partial derivative of z with respect to t, can also be easily written, and finally we can calculate, once we have these two equations or two expressions, we can easily calculate what is Jacobian matrix and determinant of Jacobian. So, now we need to look at strain displacement relation, how to express strain displacement relation in terms of finite element shape functions. Strains can be expressed in terms of nodal displacements. For axisymmetric problem, the four components of strains are defined like this. We have seen these relations earlier, only thing is now we are putting them in a vector form, all the components of strain, and the strain vector in terms of displacements can be rearranged and can be written as, can be expressed in terms of matrix and vector form, which is shown on the right hand side of the equation. So, to calculate strain vector epsilon, we need to know what is partial derivative of u with respect to r, partial derivative of u with respect to z, partial derivative of w with respect to r, partial derivative of w with respect to z. We know that since we already have the trial solution in terms of nodal displacements and in terms of finite element shape functions, we know it is easy to calculate partial derivative of u with respect to s and t, w with respect to s and t. So, we need to find a relation how to calculate partial derivative of u with respect to r and z in terms of partial derivative of u with respect to s and t. Similarly, we need to find the relation between partial derivative of w with respect to r and z and partial derivative of w with respect to s and t. This can be obtained using these relations, for which we require to know what is determinant of j. So, using these two relations, the displacement derivatives, displacement component derivatives with respect to r and z can be replaced with respect to s and t. So, writing these two equations together, we get this equation we can substitute back into the equations that we have seen for strains, where we can replace partial derivatives of displacements with respect to r and z in terms of partial derivative of displacement with respect to s and t, and rearrange it in this manner, and we can define some intermediate quantities a1 and a2, where A1 and A2 can easily be figured out by comparing the two equations. A1 is defined like this, A2 is defined in this manner. If you see the previous equation, it involves partial derivative of u with respect to s and t, partial derivative of w with respect to s and t. So, we need to make a note of how to calculate that. Since we already know parent element shape functions, we can easily find how this equation look like, and defining intermediate quantity g, which consists of partial derivative of shape functions with respect to s and t, and d is nothing but displacement component, the vector of displacements consisting of all components of displacements at all nodes. So, with these definitions, strain displacement matrix can now be written like this. So, B transpose is equal to A1 times G plus A2 times N transpose. So, we already defined what is A1, A2, G, and N transpose is nothing but a vector consisting of finite element shape functions, or matrix consisting of finite element shape functions. So, with this definition of strain, we can easily assemble what is element stiffness matrix. Element stiffness matrix is defined like this, and since B, the strain displacement matrix for the 4 node isoparametric element, 4 node axisymmetric isoparametric element that we are looking at, the strain displacement matrix B is not a constant. So, we need to adopt some kind of numerical integration scheme to evaluate this or to approximate this integral to get element stiffness matrix. So, we can use Gauss quadrature. Element stiffness matrix is evaluated using Gauss quadrature and using 2 by 2 or higher order formula if required. So, this integral for element stiffness matrix, once we decide how many integration points we choose along s direction and along t direction, we can approximate element stiffness matrix like this, which involves contribution from different integration points to the element stiffness matrix, where Si, Tj are locations of Gauss points, Wi, Wj are corresponding weights. So, this is how we can assemble element stiffness matrix for 4 node axisymmetric isoparametric element. So, now we need to look at how to get equivalent nodal vector, because finally if you want to solve the problem, we need to know what is stiffness matrix, what is force vector, equivalent nodal force, how to evaluate equivalent nodal forces. So, for that, consider the case when uniform pressure is applied along one of the sides, let us say side 1 2, that is side connecting nodes 1 2 as shown in figure below. Here there is a small typing mistake in the figure, x instead of r it is typed as x, instead of z it is typed as y. So, please read x and y as r and z. Similarly, Tx is nothing but Tr, Ty is Tz. So, now assuming uniform pressure is applied alongside 1 2, and also we should note that alongside 1 2 shape functions of nodes 3 and 4 are 0 alongside 1 2. So, along this side 1 2 shape functions n 1 n 2 are only the shape functions which are non-zero, and n 3 and 4 are 0, and also alongside 1 2, since there are only 2 nodes alongside 1 2, the shape functions of nodes 1 n 1 shape functions of nodes 1 and 2, that is n 1 and 2 are going to be linear functions. So, this information is required because we need to know what is the shape function matrix of all the 4 nodes alongside 1 2 to assemble equivalent nodal force vector. And whatever we discussed now about the shape function matrix, that is not new, this that is similar to, or that is identical to, that we already looked at when we are dealing with triangular elements. So, equivalent nodal force vector for uniform load alongside 1 2 is given by this. Q is the equivalent nodal load vector, Q T, T is for traction alongside 1 2. So, it is written as Q T, Q subscript T side 1 2, it is given by line integral shape function matrix or matrix consisting of shape functions alongside 1 2, all the 4 shape functions alongside 1 2 times traction components along radial direction and axial direction. And by substituting all the quantities, please note that in the previous equation we have 2 pi r, r can also be expressed in terms of finite element shape functions and the radial coordinates of all the 4 nodes. So, by doing that substitution and simplifying the previous integral, we get this equivalent nodal load vector, and you can easily see that equivalent nodal load vector, the components corresponding to nodes 3 and 4 are 0 because uniform pressure load is applied alongside 1 2. So, similar load vectors, equivalent load vectors can be assembled even if load is specified on the other sides 2 3 or 3 4 or 4 1. So far we discussed how to assemble or how to get the element stiffness matrix and also equivalent nodal force vector for 4 node axisymmetric isoparametric element. So, now we are ready to solve a problem. So, what we will do is we will take the problem that we already looked at in the last class, where we use 2 axisymmetric linear triangular elements to solve the problem. So, here we are going to solve the same problem using only one 4 node axisymmetric isoparametric element using the equations that we just derived. So, problem statement is as follows: find displacements and stresses in a long thick cylinder and the internal pressure, internal diameter value is given and also outside diameter value is given, material properties are specified. All the quantities are given both in SI units and FPS units. Since the figures corresponding to FPS units are round numbers, we will proceed and solve this problem with respect to the figures for FPS units. Since this cylinder is long cylinder, we can neglect the end effects, and also since this problem the structure is or geometry is satisfying axisymmetric conditions, and also loading is satisfying axisymmetric conditions. So we can easily use axisymmetric model to solve this problem, and also material properties are constant, so they also satisfy axisymmetric conditions or symmetric, all this, that is structure, geometry, material properties, and also loading are symmetric with respect to axis of revolution. So we can use axisymmetric model, and we will be using one 4 node axisymmetric isoparametric element to solve this problem. Since this cylinder is long, end effects can be neglected. A horizontal slice of 0.1 inch, that is 1.27 centimeters height, is modeled using one quadrilateral element that we discussed. And this element, the node numbers are also indicated, and also since this problem is axisymmetric problems and the nodes are constrained to have displacement only in radial direction. So displacement component at all the 4 nodes in the axial direction is 0. Also the traction is applied alongside joining nodes 3 and 1. Please note that for the node numbering that is shown in the figure on the right hand side, local node 1 is same as global node 1, local node 2 is same as global node 2, and local node 3 is global node 4, and local node 4 is global node 3. So we need to keep that in mind when we are assembling the equations. So moving in the counterclockwise directions, element nodes are 1, 2, 4, 3. Accordingly we need to note what are the radial coordinates, and also what are the axial coordinates of all the 4 nodes. Before that, constitutive matrix which is required for solving this problem is given by this. E and Poisson's ratio values are given, Young's modulus, Poisson's ratio values are given in the problem statement. So using those values we can simplify and we get this constitutive matrix. The element node numbers are 1, 2, 4, 3. So corresponding vector consisting of all radial coordinates in the radial direction and coordinates in the axial direction are given by these 2 vectors. Since we are using only one element and we adopt 2 by 2, if we adopt 2 by 2 Gaussian quadrature, we know how to get the coordinates and weights of each of the integration points. So here the calculation details corresponding to one integration points we look at, and similar operation can be repeated at other integration points, and contribution from all integration points can be taken to get the final element equation, final element stiffness. So, at integration point 1, S and T coordinates weights are shown there, and using isoparametric relation R is equal to N1 R1 plus N2 R2 plus N3 R3 plus N4 R4, we can easily find what is the R value at this integration points by substituting S and T values. Since R1, R2, R3, R4 are already known for this particular element, similarly Z coordinate for this integration point is given by this, and these are required to calculate rest of the quantities, partial derivative of R with respect to S, partial derivative of R with respect to T, similarly partial derivative of Z with respect to S, partial derivative of Z with respect to T. Once we know all these quantities, we can easily calculate what is A1, A2 and G matrices, and also shape function, a matrix consisting of all the 4 node shape functions which are required for calculating strain displacement matrix, which in turn is used for getting the element stiffness matrix. So, with these partial derivatives we can get derivative of Jacobian, determinant of Jacobian, A1 matrix, G matrix, and matrix consisting of all the 4 shape function values of all 4 nodes, A2 matrix. Once we have all this, we can substitute into this equation to find what is strain displacement matrix B, and once we have this B matrix, we can find the contribution to the element stiffness matrix from this integration point by substituting into this equation. Here K subscript 1 is used to denote contribution from first integration point to the element stiffness matrix. So, by plugging in all the values and simplifying, we get this matrix. Performing similar calculations for the other 3 integration points and adding the resultant matrices K1, K2, K3, K4, we get the element stiffness matrix which is shown here. So, we got element stiffness matrix for one element that we are adopting to solve this problem. So, now our job is to get equivalent nodal force vector. Before we do that, we need to note that traction is applied along only one side joining nodes, global nodes 3 and 1, and global node 3 corresponds to local node 4 and global node 1 corresponds to global node 1 corresponds to local node 1. So, applied load vector, load is applied along side 4 1 here. When it is written as 4 1, that is with respect to the local node numbering, and that corresponds to side 4. So, load is applied only along side 4 1 or side 4, and the radial component and axial component of tractions are given here. and also we need to note what is the length of this side. Length of side 4 is 0.5. So, substituting all these quantities into the equivalent nodal load vector, equivalent nodal load vector formula, we get this. We already discussed how to derive equivalent nodal load vector. So, substituting the coordinates corresponding to all the 4 nodes for this particular element, attraction components in the radial direction and axial direction, we get finally this equivalent nodal load vector. Please note here the non-zero components of this equivalent nodal load vector. Since Tz there is no traction applied along axial direction, the component corresponding to axial direction are all 0 at all the 4 nodes, and since load is applied in the radial direction at local node 1 and local node 4, the corresponding, except those locations, the other quantities are 0. The radial direction component at nodes 2 and 3 are 0, only non-zero are the radial component at nodes 1 and 4. So, now we got equivalent nodal load vector and we got element stiffness matrix. So, we are ready to assemble global equations and get the nodal solution. Since there is only one element, global stiffness matrix is same as element stiffness matrix, except rearrangement of rows and columns, because the way global nodes are numbered, because global node 4 corresponds to local node 3 and global node 3 corresponds to global node 4. So, we need to rearrange rows and columns corresponding to the element stiffness matrix that we derived and also equivalent nodal load vector that we derived. We need to rearrange those two, that is element stiffness matrix and equivalent nodal load vector. For that we need to make a note of what are the corresponding degrees of freedom in the local coordinate or local system and what are the corresponding quantities in the global system. So, element degrees of freedom corresponds to local degrees of freedom and global degrees of freedom corresponds to global. So, here with this understanding we need to rearrange the rows and columns, and then we need to impose essential boundary conditions. Essential boundary conditions are the displacement components at all the 4 nodes in the axial direction are 0. So, these are the essential boundary conditions, V1, V2, V3, V4 are 0. So, after rearranging based on global degrees of freedom and local degrees of freedom and imposing the essential boundary condition, since essential boundary conditions here are 0, we can eliminate the rows and columns corresponding to that location, and we get the reduced equation system. So, rearranging element equations and imposing essential boundary conditions gives following reduced system of equations, and this is a 4 by 4 equation system because only 4 degrees of freedom are unknown. So, we can solve this 4 by 4 equation system for u1, u2, u3, u4 which are nothing but radial displacement components at all the 4 nodes. So, since we know the displacement components, all the displacement components at all the 4 nodes, we are ready to calculate stresses, and before that we need to calculate strains, and then using constitutive matrix we calculate stresses similar to that we already did for plane stress plane strain problems. And here calculations corresponding to one integration point will be shown. If you require to calculate stresses and strains at any other point other than integration point, we need to know what are the corresponding values of S and T at that point corresponding to R and Z coordinates. So, once we know S and T values corresponding to the point that you are interested, you can easily calculate strains and stresses at that point once we find what is the strain displacement matrix. So, calculations of stresses for quadrilateral elements, strains and stresses vary linearly over element. Stresses at any point over element can be computed using strain displacement and stress strain relations. Since the strain displacement matrix B is available at this is already available with us because we already assembled the element stiffness matrix. Since B matrix is available at the integration points, stresses at these points can be easily evaluated. At any other point, stress evaluation requires evaluation of new B matrix at that point, for which we require to know what is S and T coordinates corresponding to R and Z coordinates of that particular point. So, now to calculate strains we need to know nodal displacements in terms of element degrees of freedom. That is, these displacement components are arranged with respect to the local node numbering. Displacement vector at this is a displacement vector which consists of the components of displacement at all the 4 nodes, and we are interested in finding what are the strains and stresses at integration points. So, the first integration point is taken and the corresponding R and Z values, S and T values are given. So, we can easily find what is R and Z values by substituting into the isoparametric mapping relation, but sometimes we require sometimes we may be knowing what is R and Z. In that case we need to back calculate what is S and T to calculate strains and stresses. So, once we have this information we can easily plug in into the strain displacement matrix S and T values, and we can calculate strains or strain vector consisting of all components of strain at this integration point, and multiplying this strain vector with constitutive matrix we get a stress vector consisting of all components of stress. So, similar stress calculations can be made at other integration points or at any point where it is required. So, basically as a part of this axisymmetric elasticity problems we looked at the governing equations for axisymmetric problems, and also we looked at derivation of element stiffness matrix and equivalent nodal load vector for linear triangular element and also 4 node quadrilateral element. So, similar equations, similar element stiffness matrix equations, and also equivalent nodal load vector equations can be derived for higher order elements such as 8 node serendipity element, following similar steps. So, in the next class we will continue with 3D elastic problems.